So basically, what we have is, remember, this energy operator, and we had the energy term, which was x squared over 2m. So that was a one-dimensional, okay, motion. We had kinetic energy, okay, corresponding to the moment when we take it. Now what we are going to do is we are going to generalize this to the x squared plus dy squared plus dz squared over 2m. And that means minus h bar squared over 2m divided by dx h bar of 5 times the derivative. Okay, del x squared. Now goes to minus h bar squared over 2m, okay, approximately. So we are going to get a three-dimensional partial differential equation. Okay, so our equation is going to look like I h bar del psi del t. Now this psi now is a function of x, y, z, and t, right? Or if you want to go to another coordinate system, which is more convenient for spherically symmetric objects like an atom perhaps, then we have to go to the spherical coordinates. Okay, so I have that equal to minus h bar squared over 2m, okay, del squared psi plus the potential energy. Now the potential energy is generally a function of position, okay, times psi. So what we will do for the purposes of this course is that usually we'll take this as no time dependence for the potential. So it's going to be just a static potential in which the particle is moving. And also, when you go to the spherical coordinates, we'll assume that this potential V also has spherical symmetry. Okay, so we'll assume that this V of vector R is equal to V of just magnitude or direction. Okay, so we have something like this. Well, what do? We do separation of variables. The time piece is, okay, we can take care of it in exactly the same way. So we just write down, we assume that this psi of r and t can be written as some, okay, space-dependent part u of r times t of t, where this separation, remember, resulted in an e to the minus energy times t type of behavior. That will still work out. So this time, instead of formally going through a process of separation of variables, I'll just assume a solution of the form e to the minus I e t over h bar, and just show that this works. Okay? So indeed, if I just substitute this object now into this psi, what do I get? Well, I'm going to get on the left-hand side, the time derivative is going to give me I h bar times, okay, the time derivative acts only on this, so it's going to give me minus I e, okay, t is being differentiated with respect to, divided by h bar, right? So u of r e to the minus I e t over h bar. Okay, so that's what the left-hand side gives me.
the right-hand side is going to be just is equal to minus h bar squared over 2m del squared, well, no more size. I'm going to replace it with u times e to the minus I e t over h bar plus v u e to the minus I e t over h bar, right? So I can just cancel these time dependencies because this is not being acted out. So I end up with this simple equation. You see this just turns into an E, which tells me that minus h bar squared over 2m, okay, del squared u, which is a function of position only, plus v u is equal to e u. Okay, so this is the time independent, okay, time independent Schrödinger equation in 3 dimensions. So it's exactly the same thing as we did in 1 dimension, except that now we have this del squared to worry about because it's now a 3-dimensional, okay, differential equation with 3 variables. Okay, so what do? We now want to solve this equation, and we'll start with the simplest cases, okay, and then build up. The simplest cases are usually in rectangular geometry. So let me just put an example here. Okay, so as an example, suppose I have something like a rectangular box. Okay, so this will be the analog of particle in a 1-dimensional box with infinite barriers. So what I'm going to do is I'm going to call this the x direction, okay, this the y direction, and that one the z direction. So it's a box placed on the origin, and it's suppose it has dimensions, okay, in the x it has length a, excuse me, in the y direction suppose this length here is b, and in the z direction it's c. So it's a box a by b by c, right? Okay, so what do I do? Okay, what do I mean by a box? So the potential is, okay, so inside the box potential is 0, outside the box potential is infinite. So the object has been confined to that okay, volume A by B by C. All right, so how do I solve this equation? Well, again, we use our standard approach of separation of variables. Okay, so separation of variables means in this coordinate system, this u of x, y, z, I'm going to say, well, this is going to be a function. The solution is going to have a form capital X of variable x only, capital Y of y, capital Z of z. And we put that into our Schrödinger equation. So what happens? Minus h bar squared over 2m. Okay, I have x derivative of all of that, but only x will be differentiated. So I'm going to get y times z, but dx, ordinary derivative, because it's only a function of x, dx, plus, okay, same thing for the y, x times z, dy, plus, okay, x and y, big Z dz. Okay, that's my Laplacian second derivative. Sorry about that. Right. Okay, second derivatives of all those functions. That plus v, well, v is 0 in the region that I want to solve, but I have to be careful about the solution because I want the wave function to go to 0 at all boundaries, right? Because wave function cannot exist outside this box. And that is, okay, that means that I have 0 for the potential, 0 times u, okay, the whole thing, okay, is equal to E times x times y times z. Okay? So I do the standard trick. I divide all of this by x and y and z. So I get minus h bar squared over 2m. Okay? D squared x dx squared over capital X minus, okay, perhaps I'll write all of them out, minus h bar squared over 2m d squared y d small y squared capital Y minus h bar squared over 2m d squared z squared over z, okay, is equal to E. Okay, now the standard argument goes that, okay, I have something which is a function of x only here. This is a function of y only. That is a function of z only. And they have to add up so that I get a constant. Okay. Now, is that... Excuse me. Okay, so how is that possible? There is nothing, okay, if I leave some function of x here, there is nothing else in these terms that is going to cancel that, right? So that means, excuse me, that means all of these terms must be equal to a constant, okay? So when I have those things equal to a constant, then I'm going to I have some hope of getting some equality here, okay? So what I'll do is, since these constants must have units of E, I'll call this thing E sub x, this one E sub y, and this one E sub z. Okay? So I have now 3 equations which look very similar. And they look something like this. Let's look at the x equation. Minus h bar squared over 2m, right? D squared x capital X dx squared is equal to E1 times x. So this is just like the particle in a box problem that we solved in 1 dimension, right? Exactly the same. And corresponds to some energy E1. Okay? So I have this x of x, which I want to exist only between, okay, according to my shape of my box here, I want it to exist only between 0 and a. It has to be 0 at other places. Okay, something like this. And I know what the solutions to such an object is, right? So if I write one more line here, d squared x, the x squared is equal to minus 2m e1 over h bar squared capital X. So what are the solutions? Sinusoidals, right? Okay, so I'm going to get sinusoidals which look like this. They have to go to 0 at the end because of the boundary conditions. So I'm going to get this, okay, a set of solutions which look like, okay, I need to normalize them, and I have sine n, okay, I'll call it n1 because I call this thing in n1, e1, pi over a x, right? So I am going to get sinusoidals which look like this, and 1 must be equal to 1, 2, 3, etc. It cannot be 0 because then the whole thing will be 0. Okay, so I have something like this, and the corresponding E1 is going to be, okay, h bar squared k squared, which is this quantity, and 1 pi over a squared over 2m. Okay, so I get a solution which looks like that. But now the equation for y and z are practically the same, right? So that means I'm going to get a similar set of solutions. So I'm going to get y of y is going to be some, okay, in general I can put some other constant here, but it's best to normalize the whole wave function rather than each one individually, but it's really the same thing as we'll see. So it's going to be sine and 2 pi over a y now. It's a function of y. Yes? B, thank you. Because size of the box we said was B. Okay, and again, and 2 is going to be 1, 2, 3, etc. Same thing for z of z, which will be c times sine and 3 pi over c, okay, y with n3 equal to 1, 2, 3, dot, dot, dot. Okay. So I have something like this. So now I can write my full, okay, time-independent wave function. My time-independent wave function, which is going to be a function of x, y, and z, is going to be just the product of these things. Okay, since I have these arbitrary constants, let me just combine them into just one. So I'll have a, okay, sine, just I'm going to repeat this, whatever I have there, and 1 pi over ax sine and 2 pi over b y and sine and 3 pi over c z. And each one is going to bring in a into the energy an ex, ey, or z, ez. Well, I have called these things ex, ey, ez, and over there I call them e1, e2, whatever. Well, okay, so I'll just correct it. This is now ex. Sorry about that. Okay, similar term for ey, similar term for ez. What is the corresponding energy? E is just this ex plus ey plus ez, right? Sum of these three terms. So I am going to get out of this the energy of the state is going to be, okay, there will be, well, very little that's common really, h bar squared or 2m times k squared, the overall k squared, which is going to be what? A pi squared, which is common to all of them, but then I have n1 squared over a squared plus n2 squared over b squared plus n3 squared over c squared.
Also, by for the time independent factorial solution, we should also multiply b and c with b capital B and capital C.
Yes, but since they are, okay, so if you like, you can put that in, but I just rename them, okay? Because A, B, C, it's just all three of them are arbitrary constants, so I can, okay, rename them. Let's call them D, so that none of them have a disadvantage. Okay. All right, so I have this. Now, I also have to normalize it, right? So that if I just want the same interpretation, the probability interpretation in 3 dimensions, now it's going to be a 3-dimensional probability density. Okay, so the normalization is going to be, okay, the integral over all places where the wave function exists, u star u dx dy dz to be equal to 1. So what do I get? Let me see if I can do everything over here. I'm going to get a d star. Okay. Then I'll get a sine squared and 1 pi over a x sine squared and 2 pi over by and sine squared and 3 pi over cz. Okay, now integrated over dx, dy, and dz. So maybe I'll expand this integral to the left and put in the appropriate limits. Okay, so dx goes from 0 to a, dy goes from 0 to b, and dz goes from 0 to c. But since it's just a product of terms like this, each integral can be evaluated separately, and we know how to evaluate these things. So magnitude of d squared times, what's the integral of sine squared from 0 to a, okay, over a number of periods? Let's say nice shortcut. Okay, so this averages to 1 over 2, and integrate from 0 to a is going to give me a over 2. This one is going to give me b over 2. That one is going to give me c over 2. So you see, I could have normalized them separately and found what these coefficients a, b, c are separately, but I get the same result. Okay, so all of this has to be equal to 1, which means that this magnitude d squared is going to be 8 over a, b, c. Okay, so I can normalize it this way. All right, so that's what I have. Now, let's look at various forms of this. We are going to use this result quite a bit, okay, because whenever we talk about, for example, let's see what happens to a electrons in a material, okay, then the material, the easiest geometry that we can consider is the geometry of a box. Okay, so we take a rectangular box and say that, okay, this is now the material, the metal, whatever that I have, and the electrons are inside it. So what are their energy states, and this is what we are going to end up with. And to make our life easier, we'll usually choose A, B, and C equal to one another, so it's going to be a cubic box. But before we get there, let's look at, I want to discuss certain special cases which are technologically important. Okay, so this is the three-dimensional case, but what type of geometries do you get in practice which are perhaps even less than three-dimensional? Well, one thing that you can get is, okay, so this is something that you can manufacture using semiconductor technology. So you take a piece of semiconductor like this, okay, and then you construct it in such a way that, okay, so you dope it with various materials so that this has a high value of the potential, V over here, okay, and then you just have a layer here, okay, so this is again high value of the potential for electrons, and in between, in the middle here, you have a very thin layer of, okay, in which you have low potentials. Okay, so these things again are usually made of, for example, things like gallium arsenide. In gallium arsenide, the electron has very nice mobility and everything, so it likes to stay in gallium arsenide. But if you dope it with something like aluminum, then it doesn't want to move there because its energy is high. So what you end up with is a box, okay, in which the dimensions, okay, so the x dimension, if you like, this is the x dimension. This is going to be A in this direction. In this direction, it's going to be B, okay, but in the z direction, it's going to be C. Okay, so this is again particle in a box, except that one of the dimensions is very small. Okay, so now what do the energy levels inside this box look like? Well, the energy levels, E is going to be h bar squared over 2m, so I'll basically write the same equation here. Okay, so it's going to be n1 squared over a squared plus n2 squared over b squared and some n3 squared over c squared. But now comparatively, compared to these things, the c is extremely small. Okay, so that means this term is very large. Okay, so if you now look at the energy levels of the electron, the lower energy levels contain N3 equal to 1. Okay, so the lower energy levels correspond to N3 equals 1. So it corresponds to a constant, okay, base potential. And then on top of that, you have these other energy levels which correspond to rather large values of A and B. So if this is something that comes out of the lab, these things are at least of the order of millimeters, right? So A and B are quite large, but the thickness is extremely small, of the order of nanometers, okay? So there's a big order of magnitude difference between the AB and C. So if I look at the energy levels corresponding to N1 equal to 1, N2 equal to 1, okay, that's going to be something over here, right? If I increase, okay, so N1 and N2 by just a little bit, that's going to be another energy level. So I'm going to get lots of energy levels corresponding to, okay, various values of N1 and N2, but N3 is equal to 1, right? Lots of energy levels which correspond to, okay, various small values of N1 and N2, but I dare not increase this N3 to 2, because as soon as I increase this N2 to 2, I'm going to get something over here, okay? So N3 equal to 2 is going to be a much higher energy, okay, much bigger energy difference than changing N1 and N2, okay? So I'm going to get, okay, again, various cases, okay, so this is lowest one here is going to be, for example, N2 equals, okay, N1 equals N2 equals 1 will be there, and then others will follow, okay? So again, I can change N1 and N2, they will make small differences in the energy, but N3 is making a big change. So typically, if you are working with relatively small energies, you don't even see this, okay? So it is as if I have a two-dimensional system. Okay, so this is a very important application. This is called two-dimensional electron gas. Okay, so I have these electrons moving in this two-dimensional space for relatively, okay, reasonable energy levels. So I don't even see this because this C is so small that all of the wave functions in the C direction are the ground state wave functions, okay? The next order wave function is a big jump in energy, okay? You can sort of see this, right? If you put millimeters here, you are going to get something of the order of, okay, 10 to the minus 3, okay? So this factor here is going to be about 10 to the 6 or something. But this number here, if you put a nanometer here, it's going to be, okay, nanometer is 10 to the minus, what, 9, so it's going to give you 10 to the 18 type of numbers there, extremely large numbers. Okay, so this separation is so large that you'll basically be working in this region where N3 is constant and you have only N1 and N2 which is changing. Okay, so you have just a two-dimensional system constructed like that. Similarly, you can do some lithography here, okay, so you can cut this thing over so that, okay, so you have perhaps something like that, okay, again, you construct this out of some semiconductor, but then when you are generating this level, again, very thin, okay, except that this time you also cut this thing into small pieces, okay, so that these things are now going like that. Okay, so this is the technology for doing this is actually quite developed because people do integrated circuits and such things using this lithography. Okay, so I don't want to do this for all over the place, but okay, you get the idea. You get, okay, basically boxes which are macroscopic in this direction. Okay, so perhaps a millimeter long, but extremely small in these directions, okay? In the, okay, the way I called it, it's going to be A and C. So A and C are very small, but the length in this direction, B, is long. So now if I look at the energetics of this system, what do I get? Well, I write the same equation again. E is equal to h bar squared over 2m. There's a squared here. Pi squared. Okay, let me group the A and the C terms together. And 1 squared over A squared plus and 3 squared over C squared. So these are the small quantities. Plus and 2 squared over B squared. So this time, these are the small quantities. And B squared is the large quantity. So in order to, so when I start to list these energy levels, excuse me, I don't know what I'm coming down with, but I hope I'll survive. Okay, so I have this case, okay, so the lowest energy levels correspond to the case when N1 and 3 are the lowest possible number, so that depending on what N2 is, I'm going to get, okay, higher energy levels as I increase N2. Okay, so as I increase N2, I get higher and higher energy levels. Okay, but then if I just venture to change even one of them, okay, let me see what's the higher band of energies. You see, I'm going to end up with an energy level over here, because as soon as I have N1 or N2 equal to 2, the other one is still 1, and that will correspond to a big jump in the energy. And again, on top of that, okay, I can start with N3 equal to 1, N2 equal to 1. Oops, it's N1 over N3, right? So I go up. As I increase N2, I get to higher and higher energies. Okay, is this more or less clear? Okay. So, okay, so this type of structure is called a quantum wire. So it's like a one-dimensional object. Okay, so you can do all types of one-dimensional, okay, physics experiments with these things. Finally, I don't want to and go over, well, maybe we should, okay. So if I now make all of these sizes very small. Okay, so if I now create a little bit of box here. Okay, so each dimension here, suppose I choose it the same so that we can play around with the energies. Okay, so it's an A by A by A box. Right? So this is now small in all dimensions. Okay, quantum, so it has quantum wavelength size dimensions in all 3 dimensions. So it's going to be perhaps a few nanometers this way, a few nanometers that way, a few nanometers that way. Such things are called quantum dots. Okay, it's an exaggeration, it's a dot, but you see, it's now this is 0-dimensional. We looked at 1, 2, and 3-dimensional. So this is actually 3-dimensional, but since it is small in all directions, we call it a dot. And these things are very interesting because now you have, excuse me, now you have all kinds of applications that come out of these things. Okay, so if I have A and A and A, what do I have? The energy will be, excuse me, h bar squared over 2m, okay, pi squared over a squared, and 1 squared plus, and 2 squared plus, and 3 squared. Okay. So now we can start labeling states more carefully. Okay, the lowest energy state is when I have the smallest possible numbers for all three of them. So the lowest energy state is going to have, so I'll call it E111, which will have energy h bar squared over 2m, okay, pi squared over a squared times 3. Okay? So, what's the next higher energy state?
7.
Well, okay. How do I put in the n1s?
6, I'm sorry. 1, 1, 2.
Okay, so E112 is going to be h bar squared over 2m pi squared over a squared. If it is 112, it's going to be 1, 1 plus 4, right? Okay, so 6 times that. So I have a bunch of energy levels building up like this, but this is not the only state which has that energy. Okay, so we are going to get 2 more states, E211 plus E121, which have the same energy. Okay, so we call this thing threefold degenerate. Okay, and then, okay, if we go one higher up, so let's just play this game one more time. What's the next one?
1, 2, 2.
Okay, 1, 2, 2, I'll trust you. E1, 2, 2 is going to be h bar squared over 2m, pi squared over a squared, and then I have 1 plus 4 plus 4. Okay, so that makes a 9. How many fold degenerate is this?
Again, 3.
Okay, 3, because I can move this 1 around to various places, which is going to be 2, 2, 1. All right. So you see, this is 6 and that's 9. So you could perhaps say that in my system, I'm going to use only lower energy, okay, states. I don't want to excite my system to higher energies, so it's going to be something at low temperatures, etc. You can then think of this as a 2-state system or a 3-state system, etc. Okay, so quantum dots are nice for doing these quantum mechanical experiments in which you have just a few states. Okay, and you see as A becomes smaller and smaller, the separation between these states are getting larger and larger. So you are going to get at some point, okay, some limitation to this. You'll say, well, okay, I'll use the lower 2 states or the lower 3 states. So if you want to have experiments which involve only few number of states, that's what you are, okay, going to do. Okay, maybe it's a good place to give a break. Let's give our break and then we'll go on.